Okay, good day, dear colleagues. We begin work on the second day of the international conference. I am pleased to announce the topic of the first speech of Daniel Lehmann, Ordinary Differential Operators and Connections, Application to Curvilinear Webs. Please, Daniel.
Thank you very much. I first want to thank the organizer first for inviting me, and also I want to thank them for organizing this conference despite of the war in the country. So can you now following page? Okay. We are given a differential operator, a linear differential operator. This means morphism or vector bundle going from the k-jets of vector bundle E into another bundle, vector bundle F over the same base V of dimension n. I have written it as an epimorphism, as something subjective, but in practice, what we require is that D has a constant rank at each point of V in such a way that we can replace F by the image of D, and finally, we can assume D to be surjective. So Q will be the rank of D, and will control the number of scalar equations which are in the partial of I did not speak about the equations. The equations will be for any section S of E, we associate the differential, we apply the operator D to the k-jet of the section, and we are looking for sections S of E in such a way we have something identically zero. So, of course, we can take the following derivatives. We have Q, the rank of D, will control the number of scalar equations. We have one equation by components of sections of F, and P will control the number of variables. Now, what we want to do is we have three goals. First, we want to give an upper bound for the dimension of the space of solutions, at least for the space of germs of solutions in a generic point of V. Secondly, we would like to find, if possible, a vector bundle around E, or script E, I don't know how it's named in English, of rank exactly pi of NKPQ, that is the wanted upper bound, in such a way that there is a bijection between solutions of the partial differential equations and the sections of round E which have a vanishing covariant derivative. And tertiarily, we wish to apply these results to the computation of abelian relations in web by curves. So please, the following. Okay, I will very often use the notation CNH for the binomial coefficient. It will be practical because CNH is the dimension of the vector space of homogeneous polynomials of degree h with n unknowns. And of course, as you see, the rank of all polynomials is the sum of the CNL for L going from 0 to H. So we have the formula by we can homogenize a non-homogeneous polynomial by adding one more variable. In such a way, we have the formula which is we called sum of the CNL from L equals 0 to H. This is equal to Cn plus 1H. Okay. Now, of course, also we can have a prolongation of each partial order differential equation by taking derivations, and the kernel of dH will be the set of formal solutions at order H. The general method that we will use for the moment will be to look on the tower of the formal solutions at order H, with H increasing up to infinity. And if we will study, and if possible, we will estimate R infinity, the formal series, the formal solutions. And if there is analyticity, we know that the germs of solutions has a dimension at most equal to the dimension of the formal solutions. So this is the principle that we want now to study how we move the dimension, the rank of RH by taking one more expansion. Then we want to study the following, please. Next page, please. Okay, we want to study we give an element in a formal solution at order H-1, and we want to look what are the formal solutions at order H which project onto the previous one. Can you even, thank you, still more? Still, well, all right. We want to study the system. This is a linear system of equations. We are looking on the formal solutions at order H, which project onto a given solution at order H-1. And this is a linear system of equations, and we want to estimate a number of equations. Please go further. I cannot, I cannot handle myself. Okay. The number of equations will be Q times. No, please, it's all right. The number of equation, what will be the rank of this bundle SH minus K T star of V, that is the polynomials with coefficients in F, that is Q times Cn H minus K, and the number of unknown will be the rank of the formal of the homogeneous polynomials of degree H with coefficients in E, so that is P Cn H. So what we want to do is to assume that the system has maximum rank, which means that the principal, please, next page. Okay. So we arrive to do our principal definition. DSC is said to be ordinary if all the system have a maximal rank, which means that the principal symbols of the differential of the successive differential operator have maximal rank. This is the minimum, the inf of the two dimensions that we have given before. Therefore, if P over Q, we have to compare P over Q with the function phi of H, which is the ratio CNH minus K over CNH. If P over Q is smaller than phi of H, then the system is overdetermined and has at most one solution. If, on the contrary, P over Q is at least equal to phi of H, that means that the number of equations is not too big, then the solutions of the previous linear system is an affine space of dimension, the number of variables minus the number of equations. So we have to look on this function. Please go to the following page. Following. Yes, thank you. The function phi of H, that is the ratio from CNH over CNH minus K over CNH in function of H is, please, yeah, okay, thank you, is increasing from 1 over CNK to 1 when H goes from H to H. So we have three situations. Our P over Q is smaller, following previous page, previous. If Q over P is Q, if Q is smaller than P, we have very few equations, then the rank of RH increases with each H, and the dimension of formal solution may be infinite. So is infinite. So it may happen that the solutions is infinite, is a space of infinite dimension. Now, if Q is strictly bigger than Q, that P, C, and K, there are too many equations, and there is only the trivial solution, 0. And the interesting situation is, of course, the mean domain when Q is strictly bigger than P, and in between, and at most P, C, and K. So if you go back to the next page, you have the diagram, please. In the yes, thank you. You have on the diagram we see the three zones. If P over Q is between P over Q and 1, then it is this situation which is interesting. And what happens is that the system sigma of R H minus 1 has increased, the dimension will increase up to some rank H0, which is the highest H, which the highest H, it's difficult to show it. Can you, yeah, thank you. Can you show the okay. We are looking, well, okay. What will happen, I summarize. What will happen is that the rank of RH will increase up to H equal to H0. H0 is the H which appears on the diagram when P it is the highest H, such that P over Q is bigger than phi of H. So we are interested now with the third case, which is now here. And what happens is summarized when you are looking on the behavior of the sequence. The rank rho H of RH is a vector bundle, and its rank is increasing up to the rank H0, and after, all systems are overdetermined, so the rank there is at most one solution at the system for h bigger than h0. So after, the rank may only decrease up to rho infinity. And therefore, we conclude by the proposition 2, the rank of formal solutions is at most equal to the rank of RH0, which is easy to evaluate and which is given by the formula which is in the theorem 1. Therefore, if we have if the system, if the framework is analytic, real or complex, holomorphic or real analytic, then we know that the dimension of the germs of solutions is at most equal to the dimension of the formal solutions. And so we have an upper bound which is given by the rank rho h naught, which is given by this formula, easy to compute. Please show me the. Okay. Now, yeah, is it possible to rest? Okay. What we call we give now the second definition. It may happen that P over Q is exactly equal to phi of H0. In that case, RH0 over RH0 minus 1 is an isomorphism. And so we can look on the inverse isomorphism, which composed with the natural inclusion of RH0 into the one jets of RH0 minus 1 defines a connection on the bundle. Can you all right, thank you. Good. All right. We compose the inverse of this isomorphism from the projection, the inverse of the projection of RH0 over RH0 minus 1. We take the inverse. We compose with the natural inclusion of RH0 into the one jets of RH0 minus 1. And so we get a splitting of the exact sequence of the projection J1 RH0 minus 1 over RH0 minus 1. And such a splitting defines a connection on RH0 minus 1, which has precisely the dimension, don't move, which has precisely the wanted dimension, the wanted rank. And of course, no, please go back. Right, all right, no, don't move. The covariant derivative of a section of RH0 minus 1 is the difference of J1 of this section with the image of this section by the splitting. Of course, this difference is in the kernel, T star of V tensor RH0 minus 1, and so defines a connection which is analytic if the framework is analytic, but here we do not need, again, we don't need analyticity. This is available in the framework in the real framework, only differentiable, C infinity differentiable, or also in the holomorphic framework. So we get the theorem 2. Please, can you show the theorem 2? Thank you. We have a bijection between the solutions of the partial differential equations and the sections S of RH0 minus 1 which is the script E that was announced at the beginning, in such a way that it's equivalent to say that S is that a section small s is a solution of the partial differential equation, or to say that is H0 minus 1 jet has a vanishing covariant derivative by the previous connection. Therefore, the dimension of the space of solution is at most equal to the rank of the bundle, and the rank of the bundle is precisely rho of H0 minus 1, but rho of H0 minus 1 is equal to rho of H0 since we have an isomorphism in this case. And what is interesting is that we don't need to exhibit the solutions to know that the dimension of the germs of solution is optimal, is maximum, because for that it is necessary and sufficient that the connection has zero curvature. So the curvature will be an obstruction for the dimension of the germs of solution to be maximal. Please, next.
May I ask you the question here?
Yes.
You said that in this case, okay, if we have a section of this, then we can write this formula, and this gives you the corresponding connection. But this section, this isomorphism, it also holds in C-infinity situation or only in analytic?
What happens is that because the formula which is recalled RH0 is the intersection in J1 of JH0 minus 1 capital A of the two sub-bundles which are written here, the splitting goes through RH0 because the splitting goes through RH0. Therefore, it's equivalent to say that S is a solution, S, the small s, a section of capital A is a solution of the wanted equation, or to say that is GH0S is H0 jet as a covariant derivative. The both are equivalent. This is because the formula which is recalled here.
No. The question is, I understand that if we have a section from RH0 minus 1 into 1 jets, if we have a section, then we can write this formula nabla sigma, this formula. But the question is, you say that this also holds in C-infinity situation, or only in analytic?
Yes. All what we used the analyticity previously only for saying that the germs of solution, the dimension of the germs of solution is at most equal to the dimension of the formal solutions. But here we know this construction here is available in the differentiable case. We don't need analyticity for making this construction. We have, once we know that the section that we have a bijection between the solutions and the sections of round E, which have a vanishing covariant derivative, when we know that, the dimension of the space of solutions cannot be bigger than the dimension of the bundle around E. So we don't need analyticity now in this calibrated case. In the non-calibrated case, we need analyticity. But in the calibrated case, we don't need it anymore. Do I answer to your question or not?
Sorry, but the question is, so this U exists also in C-infinity situation? Yeah, that was just the question. This U section of this from jets. So you
this construction works as well.
Okay. So understand. Thank you.
So I want now to speak to say a word during the remaining time about the application to curvilinear webs. A curvilinear means webs by curves. That is, webs of codimension n-1 on a n-dimensional manifold. That is, webs by curves. That is, what is a web? Locally, it's a family of a D web, where D is an integer, is a family of D foliations by curves on V. And we assume D strictly bigger than the dimension of the manifold. And we assume also that all these foliations are in general position, each one with respect to the other one. That means that we can generate these foliations by vector fields by giving D non-vanishing vector fields, one for each foliation. And we assume that at any point of V, when we take n of these vector fields at a point, n among the Ds, they are linearly independent, whatever be the n, the subfamily of n among the Ds. That means general position. So what is an abelian relation? An abelian relation is a family of n-1 forms on V. What we want is that the sum of this form, eta lambda, lambda going from 1 to D, the sum of this eta lambda is 0, and each eta lambda is del lambda basic. That means that the interior product of eta lambda by del lambda is 0, and the Lie derivative of eta lambda by del lambda is also 0. There is a mistake it is L del lambda eta lambda equal to 0. The Lie derivative of eta lambda with respect to the vector field del lambda. And so what does that mean in practice? In practice, a foliation can be seen locally as a fibration over a transverse manifold, and locally a del lambda form, del lambda basic form with respect to del lambda basic form is a form on the transversal, is the inverse image by the local projection of a form on the transversal manifold, and it does not depend on this transverse manifold. But what we can now construct a bundle E. Okay, I shall just summarize here. I don't enter in the detail. They are explained here, but we have three conditions to define the abelian relation. The interior product is 0 of eta lambda by del lambda is 0. This is something which has a meaning at each point, depending only on the value of eta lambda at the point. The sum of the eta lambda is 0. This also has a meaning at each point, depending only on the value of eta lambda at the point. So these two first conditions allow to define a vector bundle E whose description is described here. And we get a vector bundle. But the third condition, which is that the Lie derivative of eta lambda by del lambda is 0, this third condition depends not only of the value of the form at the point, but also of its one jet. Therefore, it defines a differential operator of order 1. Please, the following page. So we define, the end of the previous one, please. Thank you. So abelian relations are also solutions of the partial order differential equation ds equal to 0, where S is a section of the previous bundle, and D being given the D of a family of eta lambda section of E is given by the family of the Lie derivatives. Please, next page. Thank you. So we get an order partial differential equation. The order k is 1. The rank of E is d minus 1, and the rank of the operator is d minus 1. It's not d because we can see that if we can see that the sum of all these equations will be identically 0. So we can omit one of them. And what happens in that case is that this operator is always ordinary, and moreover, it's always calibrated. So all what we did before can be done. And when we look on the upper bound, we get a number which is written here. The upper bound, we had a general formula which gives this value in this particular case. And this value is exactly to the bound which was already given by Damiano in the years 1988, I think, which is the maximum rank of the web. The rank is the dimension of the space of abelian relations. So we have we recover this bound given by Damiano. But what is interesting is that now we have also the connection that we described in the general case, and we can build it in this particular case. And for the web to have its maximal rank, it is necessary and sufficient that the curvature of the connection that we can build for the web be 0. And this is applied, please, next. Okay, we want to look on this example. It is to understand what is this example. It is an n+3 web of curves in the n-dimensional manifold. It is on an open set of the n-dimensional projective space, real or complex according to the framework. And in the planar case, in the case n equal 2, it is a ball which has been defined in the years 1930 by Ball. You have 4 points in the plane in general position, and you look on the 5 web, given the 4 first foliations is the pencil of lines through each of these points. So the pencil of lines through one of these points is a foliation. You have 4 such foliations, and the 5th one is the pencil of conics through these 4 points. And more generally, here we take n plus 2 points in general position in the projective space. This means that they constitute a projective frame in the projective space. We take a pencil of lines, of straight lines through each of these n+2 points. So we get the n+2 first foliations, and the last one is the family, the foliation given by all rational algebraic curves of degree n going through these n+2 points. There is a unique such pencil of rational curves. the cubics in the conics in the plane, cubic in the three-dimensional space, and so on. So please, thank you.
Minutes. 5 minutes, Daniel.
Okay, thank you. Damiano claimed they all have maximal rank. He proved that for n even, but made a mistake in the case where n is odd, and Pirlio proved it for n odd. But this is not at all very easy, even in the planar case, to exhibit. When they exhibit abelian relations, but some ones are very difficult to understand because the polylogarithm have to occur in the definition of this abelian relation. So it exhibits these abelian relations to prove that the rank is maximum is not easy. And what we did is to compute by Maple, using a program on Maple, we compute the curvature and proved that this curvature is 0, at least for n equal 2 or n equal 3. For our program is available for n bigger, but the time of computation is too big. So I have not the time to let run such a program to show you that we get 0 curvature, but so we prove what, at least in this case, without to use the polylogarithms, we prove the maximality of the rank. So I shall just show, please, the references. Thank you very much. And okay, I stop now.